Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have a circle that is inscribed by a semicircle, and we know that line segment CD equals to 3 units, line segment BD equals to 4 units, angle CDB, this angle is a right angle, it is equal to 90 degrees, and we want to find out the radius of this small circle. Okay, so first of all, we'll start with a construction. We'll complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment CD until it touches the circle. And we will define the touching point of the extended line segment CD in this circle as point E. We know that CD is a straight line, and then we extended the straight line CD by a straight line, so CE, the result is CE, that is also must be a straight line, because when you extend a straight line by a straight line, the result must be a straight line. So CE is a straight line. This line segment CE is a straight line. And we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles must be equal to 180 degrees. So which angles we have at this side of the straight line C at point D? We have here 90 degrees at angle EDB. So write it down. So actually 90 degrees plus the size of angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that I mentioned, that the sum of the angles on one side of a straight line is equal to 180 degrees. Okay? So we will subtract 90 degrees from this equation, and we will get that angle ADB, the missing angle, is equal to 180 degrees minus 90 degrees, it is 90 degrees. So this angle is a right angle, it is equal to 90 degrees, angle ADB. So here we know that the semicircle that we created here, the second semicircle that completed the original semicircle to a circle, is a mirror image of the original semicircle. I will repeat again. This, the second semicircle that we created from the original semicircle, is a mirror image of the original semicircle. And we also know that here angle CDB B equals to 90 degrees, and then again EDB also equals to 90 degrees. And we know that the semicircle, this semicircle is a mirror image of the original semicircle. Therefore, we can conclude from it that CD is equal to DE. CD is equal to DE by symmetry. CD equals to DE by symmetry. I repeat again. CD equals to DE because of the fact that this semicircle that we created is the mirror image of the original semicircle. So when we extended the straight line CD by the straight line, we created the mirror image of the straight line CD. And when you create a mirror image of any straight line or whatever you create, the length doesn't change in the mirror image. So because of the fact that DE is also the mirror image of CD, we know that the length of the original object and its mirror image doesn't change, and the only thing that is changed is the direction. The direction is in the opposite side, but the length of those two line segments, that one is the mirror image of the other, will not change. That is to say, the length of those two line segments are equal to each other because of the fact that DE is the mirror image of CD. So we can write down that DE is the mirror image of CD because the mirror image, it is always in the same size as the original image, but the direction is the opposite direction. But the length didn't change at all. So CD equals to DE by symmetry. DE is the mirror image of CD, therefore the lengths of those two line segments must be equal to each other. They are not in the same direction, but their lengths are the same lengths. Okay? Actually, if we fold the two semicircles, then point E will merge with point C, and point D is the common side. That is to say, that for that reason CD equals to DE by symmetry. Okay, but CD equals to 3 units according to what is given us the question. So CD equals to 3 units, it is given us the question, and from this equation DE equals to CD equals to 3, we will derive that DE is also equals to 3 units. DE is equal to 3 units. Okay? Here DE equals to 3 units. In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, if two chords intersect with each other inside the circle, then the following equation is true. So actually we have this circle and we have two chords that intersect with each other inside this circle. The first chord is called AB. This is called AB that intersects with chord CD. This is called CD. So here the red chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So in this case, the following equation is true. Actually here, AO times OB equals to CO times OD. I repeat again. If chord AB intersects with chord CD and the intersection point is inside the circle is point O, then the following equation is true, that AO times OB equals to CO times OD again. AO times OB equals to CO times OD. Okay, so we actually can implement rule number 1 in our drawing, because in our drawing we have chord AB. This is chord AB. This is chord AB that intersects with chord CE. This is chord CE. And the intersection point is at this point, point D. I repeat again. Chord AB intersects with chord CE at point D. I write it down. Chord AB this chord AB intersects with chord CE, this chord CE at point D. Point D is the intersection point of chord AB with chord CE. I will repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, all the requirements of rule number 1 are made. Therefore, we can implement rule number 1 in our drawing. That is to say, we get that AD over DB equals to CD over DE. Again, AD over DB equals to CD over DE. I will write it down. According to rule number 1, AD times DB equals to CD times DE. I'll repeat again. AD times DB equals to CD times DE. According to rule number 1, of course. So here AD is the missing line segment, so we'll leave it as it is. Times dB. dB is equal to 4 units according to what is given as the question. So we'll substitute dB by 4 and it is equal to CD. CD equals to 3 units according to what is given as the question. So we'll substitute CD by 3 times DE. DE is also equals to 3 units according to what we have already found out. So in conclusion, we found out that according to rule number 1, AD times 4 equals to 3 times 3. 3 times 3 is 9, so 4 times AD equals to 9. Here we divide this equation by 4 and we get that AD equals to 4 over 9. AD equals to 4 over 9. So here we can write down that AD equals to 4 over 9. We also know that AB is the diameter of the circle and also the diameter of the semicircles. Okay, AB is the diameter of the circle and the diameter is twice as long as the radius. So we'll divide the diameter by 2 in order to find out the radius of the big circle. We'll define the radius of the big circle as capital R. So here we get that the radius of the big circle that is defined as capital R, it must be equal to the diameter that is AB over 2, because the diameter is twice as long as the radius, or AB equals to 2 times the radius. Okay, so what is the length of AB? Here AB equals to AD plus DB. AD plus DB, all divided by 2. So here AB equals to AD. Here AD is 4 over 9 plus DB. DB equals to 4 units according to what is given us in the question. And then we have to divide it by 2. Here we will multiply 4 by 4 by here it is actually AD is 9 over 4. AD is 9 over 4. Made a mistake, AD is 9 over 4. AD is 9 over 4. Okay, here AD is 9 over 4. So here also AD is 9 over 4 plus DB, it is 4 over 2. So here we will multiply 4 by 4 and then we will divide it by 4 in order to have a common factor with this expression. So we will get that 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25 over 4, and 2 will move to the denominator. So in the denominator we have 25 over 4 times 2 is 8. So in conclusion, we found out that R equals to 25 over 8 units. This is the radius of the big circle, that is also the radius of the semicircles. Is equals to 25 over 8. It is a little bit greater than 3 units. 3 and 1 over 8 units. Okay? So, here we will define the center of the big circle as P, and we define the center of the small circle is Q, and we will define the point of tendency of tangent DB with this small circle is point M. Point M is the point of tendency of tangent DB with this small circle. Then from point Q, we'll draw radius to point M, that is the point of tendency. Here QM is the radius of the small circle because of the fact that line segment QM starts from the center of the small circle, that is to say from point Q, and ends at point M, that is a point on the small circle itself. This is exactly the definition of a radius. And we'll define the radius of the small circle as small r. So here we have the radius QM is drawn to the point of tendency. I'll repeat again. Here the radius QM of the small circle, that is small r, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent DB will be perpendicular to the radius MQ. Again, DB is perpendicular to MQ, that is to say this angle equals to 90 degrees, and this angle will also equal to 90 degrees. According to the rule that I mentioned, that whenever a radius is drawn to the point of tendency, then the radius will be perpendicular to that point, to that tangent. In this case, the radius QM perpendicular to the tangent PB, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from the center point Q, the center of the small circle, that is point Q, we'll draw the radius to the point of tendency. Here we define the point of tendency of tangent CD with this small circle as point L. Again, QL is the radius of the small circle, that is to say it is equal to small r. So here we have the radius QL that is drawn to the point of tendency, that is to say it is drawn to point L, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CD will be perpendicular to radius BQ. Again, CD is perpendicular to BQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees, according to the rule that I have already mentioned. And tangent to a circle is perpendicular to the radius that is drawn to the point of tendency. In the next step, we will focus on quadrilateral LQDM. In quadrilateral LQDM, quadrilateral LQDM, this quadrilateral, we have 1, 2, 3 right angles. Again, in quadrilateral LQDM, we have 1, 2, 3 right angles. The sum of right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle inside quadrilateral LQMD, that is angle LQM, this angle. In total, the sum of those four angles inside quadrilateral LQDM must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we'll subtract 270 degrees from this equation, and we'll get that the missing angle LQM, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that angle LQM is a right angle, it is equal to 90 degrees. Therefore, quadrilateral LQMD has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So we can write down that quadrilateral LQDM is a rectangle. Okay, and we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of rectangle LQDM, they are equal to each other. That is to say, LQ is equal to DM. LQ equals to DM. But we already found out that LQ equals to R, it is the radius of the small circle. LQ equals to R, and from this equation R equals to LQ equals to DM, we will derive that DM is also equals to R. DM is also equals to R. So I can write down here that DM is equal to R, is the radius of the small circle. And what is the value of the small line segment DP? The value of the small line segment DP from the drawing, you can see that the value of the length of the small line segment DP, it will be equal to DB minus PB. DB minus PB equals to the length of the small line segment DP. Again, DB minus PB equals to DP. I'll repeat again. The length of the short line segment DP equals to DB minus PB. So actually DP equals to DB. According to what is given us in the question, DB equals to 4 units, so we substitute DB by 4 minus PB. PB, what is PB? P is the center of the circle. B is the point of the circle itself, and this is exactly the definition of a radius. That is to say, PB is the radius of the big circle that is equal to capital R. So we substitute PB by capital R because PB is the radius of the big circle that is equal to capital R. So in conclusion, DP equals to 4 minus capital R. But we have already found out that the value of the radius of the small circle, the radius of the big circle, capital R, equals to 25 over 8 units. Okay, so we can substitute R by 25 over 8 units. We get that DP equals to 4 minus 25 over 8 units. So DP equals to 4. Here we'll multiply 4 by 8 and then we'll divide it by 8 in order to have a common factor with this expression. So 4 times 8 is 32. 32 minus 25 over 8. So 32 minus 25 is 7. And here I actually found out that DP equals to 7/8. DP equals to 7/8. So we can write down here that the drawing that the length of the short line segment DP equals to 7/8. Okay. And now what is the length of PM? From the drawing it is really easy to see that PM equals to DM minus DP again. DM minus DP equals to PM. DM minus DP, DM minus DP again, DM minus DP equals to PM. I'll repeat again, PM equals to DM minus DP. So PM this line segment equals to DM equals to R, it is the radius of the small circle, it is equal to the radius of the small circle, that is small r, so we'll substitute DM by R, minus DP. We've already found out that DP equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. So we can write here that PM equals to small r minus 7/8. 7/8. Okay. In the next step, we will connect together point P and Q, and we will define the point of tendency of the small circle with the big circle. This point is point S. We actually, here I will draw the line here. Actually, here PS, what is the length of PS? The definition of PS. P is the center of the big circle. S is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PS equals to capital R, that is actually equals to 25/8. 25/8. But in the next step I will present to you a new rule that is actually rule number 2. According to rule number 2, the straight line that connects the centers of two circles with an internal length between them passes for the launch point. So here, according to rule number 2, the straight line that connects the two centers, the straight line that connects the centers of two circles with an internal lunge between them passes through the lunge point. And the lunge point is the point of tendency between the two circles. Lunge point is the point of tangency, or the touching point also between the two circles. So here we have between the big circle and the small circle, we have an internal lunge between the big circle and the small circle. Why? Because of the fact that the small circle is tangent to the big circle with point S. Point S is the point of tendency, or the touching point between the small circle with the big circle. So in this case, because of the fact that the big circle is inside, the small circle is inside the big circle, it is defined as internal lunge. Okay, the two circles touching each other internally or tangent to each other internally. And in this case, the distance between the centers of the two circles is PQ. Why it is PQ? Because P is the center of the big circle, Q is the center of the small circle. PQ is the line segment that connects between the centers, P and Q. And according to rule number 2, this line segment PQ passes through point S. That is to say, points P, Q, and S are located on the same straight line. That is to say, PQS is a straight line. So here PQS is a straight line, and therefore PQS it will be defined as the radius of the big circle, because it starts from point P, that is the center of the big circle, and there's at point S, that is the point of the big circle itself. This is exactly the definition of a radius. So we get that PS is the radius of the big circle, and the real issue here is that PS, that is the radius of the big circle, passes through point Q, that is the center of the small circle. This is the real thing in rule number 2, that the radius of the big circle, that is PS, passes through point Q, that is the center of the small circle. And therefore, so we know that PS equals to capital R, and QS, Q is the center of the small circle, S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. So PS equals to capital R, and QS equals to small r. In conclusion, PQ, this line segment PQ, from the moment it is very easy to see that PQ equals to PS minus QS. PS minus QS. Again, PQ equals to PS minus QS. Okay? PQ equals to PS minus QS. We have already found out that PS is the radius of the big circle that is equal to capital R. So we substitute PS by capital R, and QS, we already found out that QS equals to the radius of the small circle, that is small r. So in conclusion, we found out that PQ equals to capital R minus small r, that is to say PQ equals to capital R, that is 25 over 8, minus R, small r, that is the radius that we are looking for, the radius of the small circle. So in conclusion, we found out that PQ equals to 25 over 8 minus R. So we can write down here that PQ equals to 25 over 8 minus R. So now we can implement the Pythagoras theorem in the right triangle PQM, and we find out the value of small r, that is the only missing variable in this triangle. By implementing the Pythagoras theorem on the green right triangle QPM, we will find out the value of small r, that is the only missing variable in this right triangle. So I'll copy the right triangle PQM and we'll implement the Pythagoras theorem on the right triangle PQM. Okay? So this is the round triangle QPM that I copied from the original drawing. We have already found out that the hypotenuse PQ equals to 25 over 8 minus small r. We have already found out that side PM equals to r minus 7/8. And here we know that QM is the radius of the small circle because of the fact that it starts from point Q, that is the center of the small circle, and ends at point M, that is the point on the small circle itself. And this is exactly the definition of a radius. That is to say, QM is the radius of the small circle that is equal to small r. So this is the right triangle QPM. We follow of its sides. We will implement the Pythagoras theorem on the right triangle PQM. So by PT, the progression for Pythagoras theorem, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ. Consider the hypotenuse is PQ. Therefore, the square of the hypotenuse is PQ squared. And it is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to PM squared plus QM squared. Okay? This is true according to the Pythagoras theorem. So according to question number 1, PQ squared equals to PM squared plus QM squared. We already found out that PQ equals to 25 over 8, 25 eighths minus r. So PQ squared will be equal to 25 over 8 minus r squared. And it is equal to PM squared. PM equals to r minus 7/8. So PM squared will be equal to r minus 7/8 squared plus QM squared. QM equals to r, so QM squared will be equal to r squared. So in conclusion, we found out that according to equation number 1, 25 over 8 minus r squared equals to r minus 7/8 squared plus r squared. Here we will open the brackets on both sides of this equation number 1. And we get that according to equation number 1, 25 over 8 minus r squared equals to 25 over 8 squared. That is 25 squared is 625 over 8 squared, it is 64. So it is 25 over 8 squared is 625 over 64. Plus r squared minus 2 times 25 over 8 times r. According to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. We will open in the same way the brackets this on this side of equation number 1. Here we'll get that r minus 7h squared equals to r squared plus 7h squared is 49 over 64 minus 2 times r times 7h plus r squared. So here, first of all, we have r squared on both sides of the equation, so r squared will get cancelled. So what is left from equation number 1 after we cancelled r squared? What is left is actually this side of the equation we have 625 over 64. Here we divide this equation, both the numerator and the denominator of this expression, by 2. Minus 2 over 2 is minus 1, so in the numerator we have only minus 25r that is left. In the denominator we have 8, so 8 over 2 is 4. So in conclusion, this expression equals to minus 25r over 4. And in the other side of the equation we have 49 over 64. Here we have minus 2r times 7 over 8. We divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so in the numerator we left only with minus 7r. In the denominator we have 8, so 8 over 2 is 4. So in conclusion, this expression equals to minus 7r over 4 plus r squared. Here we will multiply this equation number 1 by 64, and we'll get that according to equation number 1, over 64 is 1, so we left only with 625. Minus 64 over 4 is minus 16. So this expression equals to minus 16 times r, and we have to multiply it by 25. Which is minus 16 times 25r. That is equal to 49 over 64 times 64 is 49. And we have minus 64 over 4 is minus 16. So this expression equals to minus 16 times 7r. And r squared times 64 is 64r squared. Okay. So according to question number 1, 625 minus 16 times 25r is minus 400r. And it is equal to 49 minus 16 times 7 is minus 112, and this expression equals to minus, in total, to minus 112r plus 64r squared. So we will add to this equation number 1, 400r, and we get in this side of the equation we have 625, 4 plus 400r minus 400r is 0, so this will get cancelled, and we have in the other side of the equation 49, and we have 400r minus 112r is plus 288 r plus 64r squared. Here we subtract 625 from this equation, equation number 1, and we get that according to equation number 1, 64r squared plus 288r, and we have 49 minus 625. Yeah, 49 minus we have 49 minus 625 equals to minus 576, and 625 minus 625 is 0. So in conclusion, we found out that according to equation number 1, 64r squared equals to 288r minus 576. Here we will divide this equation number 1 by 32, and we'll get that according to equation number 1, 64 over 32 is 2, so this expression equals in total to 2r squared. 280r minus 34, 288r over 32 is 9r. And there minus 576 over 32 is minus 18. That is equal to 0. So here we have a quadratic equation, and the variable that we are looking for in this quadratic equation is r. So x equals to r. The coefficient a equals to 2. The coefficient b equals to 9. And the coefficient c equals to minus 18. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a, when a, b, and c are the coefficients of the quadratic equation. In our specific equation, we know that the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. So we'll put the data inside the equation, and we'll find out the value of the values of r, because x equals to r. So we substitute x by r, and r equals to minus b. B equals to 9, so minus b is minus 9, plus minus square root of b squared minus 4 times ac. B equals to 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 18, over 2a. A is 2, so 2a is 2 times 2, that is 4. So here r equals to minus 9 plus minus minus 18 times 2 is minus 36, and minus 36 times minus 4 is plus 144. So inside the root we left only with 81 plus 144, all divided by 4. So here we get that going to question number 1, R equals to minus 9 plus minus 81 plus 81 plus 144 is 225. So inside the root we left only with 225, all divided by 4. So R equals to minus 9 plus minus, the square root of 225 is 15 over 4. So here we have two solutions that are possible for R. The first solution for R is that R equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24 over 4 is minus 6. So if we know that according to the first solution, R equals to minus 6. That is a negative number, but because of the fact that R is defined as the radius, the length of the radius of the small circle, so R as a length must be a positive number. So here I write it down that R is a length, and as a length it must be a positive number. It cannot be equal to minus 6, that is a negative number, so we cancel the solution and we left only with the second solution for R, that R it is equal to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4, so R equals to 6 over 4. We divide both the numerator and the denominator of this expression by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that R equals to 3 over 2 units, so we can represent it also as 1.5 units. Okay? So I repeat again, the answer to the question is that the radius of this small circle, that is to say small r, it is equal to either 3 over 2 units, or in terms of numbers it is 1.5 units. Okay? So in the next step I will summarize the lecture. Okay? So we have here a circle that is described by a semicircle. We know that side CD, this side equals to 3 units, side DB equals to 4 units, and angle CDB equals to 90 degrees. And we want to find out the radius of this small circle. Okay? So in the first step, we actually made a construction. We completed the semicircle to a circle. Here we completed this semicircle to a circle, and we extended line segment CD by a straight line until it touches the circle at this point. Point E is the point of contact of the extended line segment CD in the circle. Okay? So actually CD is a straight line, and we extended the straight line CD by a straight line. When you extend a straight line by a straight line, the result must be a straight line. So the result that is CE must be a straight line. So we know that CE is a straight line, and we have the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on this side of the straight line CE, it's point D, then the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. Which angles we have at this side of CE at point D? We have here 90 degrees and angle EDB. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned, that the sum of the angles on one side of a straight line equals to 180 degrees. Again, 90 degrees plus angle EDB in total, they must be equal to 180 degrees according to the rule that I mentioned. We subtracted 90 degrees from this equation and we found out that the missing angle EDB equals to 90 degrees. So here angle EDB equals to 90 degrees. And here, actually, by doing the construction, we completed the semicircle to a circle. So actually, we created here another semicircle that is actually the circle composed of two semicircles. Okay? And this semicircle is a mirror image of the original semicircle. I repeat again, this semicircle is the mirror image of the original semicircle. Okay? And you know that angle CDB equals to 90 degrees and angle EDB also equals to 90 degrees. So when we extended the straight line CD by a straight line until it touches the circle's point E, we actually created the mirror image of line segment CD. Because of the fact that this semicircle is the mirror image of the original semicircle, by extending line segment CD by a straight line, we created the mirror image of CD, that is DE. That is to say, DE is the mirror image of CD. And we know that the mirror image, it has exactly the same length of the image itself. Okay, when you look at the mirror, you see yourself exactly the same dimensions that you, in reality, you see it in the mirror, but in the opposite side. So CD must be equal to DE, but it is the side is the opposite side. Why? Because DE is the mirror image of CD. Okay? And because of the fact that DE is the mirror image of CD, the length of those two line segments must be equal to each other. That is to say, the mirror image DE must be equal to the original image of CD. Okay? CD equals to DE because DE is the mirror image of CD, and the mirror image is always the same side of the image itself, but the direction is the opposite direction. So CD equals to DE by symmetry. Because of the fact that DE is the mirror image of CD, they must be equal to each other by their lengths. So they are equal to each other by symmetry. And here we know that CD equals to 3 units. It is given as the equation that CD equals to 3 units. And from this equation 3 equals to CD equals to DE, we will derive that DE is also equal to 3 units. Okay, here we can write down that DE equals to 3 units. And then I presented to you rule number 1. According to rule number 1, if two chords intersect with each other inside a circle, then the following equation is true, that AO times OB equals to CO times OD. So here we have this circle. Inside this circle we have chord AB, this chord, the red chord, intersects with chord CD, the blue chord, at point O. The point O is the intersection point of chord AB with chord CD, and the intersection point is inside this circle. Okay, in this case, if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB intersects with chord CD at point D. Again, chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. So all the requirements of rule number 1 are met. Therefore, we can implement rule number 1 in our drawing. And according to our drawing, we get that AD times, so I repeat again, chord AB intersects with chord CE at point D. Therefore, we can implement rule number 1 in our drawing. That is to say, according to rule number 1, we will get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. Here, AD times DB equals to CD times DE according to rule number 1. AD is the line segment that we are looking for. DB is equal to 4 units, therefore we substitute DB by 4 units. CD equals to 3 units. DE is also equal to 3 units. So in conclusion, we found out that according to rule number 1, AO times 4 equals to 3 times 3, that is 9, or 4 times AD equals to 9. We divided this equation by 4 and we found out that AD equals to 9 over 4 units. So we can write here that AD equals to 9 over 4 units. Now we can calculate the length of the, we know actually what is the length of the diameter AB. The diameter AB of this circle equals to AD plus DB. AD equals to 9 over 4. DB equals to 4. So in conclusion, the diameter AB equals to 9 over 4 plus 4. And if we divide the diameter by 2, we'll get the radius of the big circle. Okay, the radius of the big circle equals to the diameter over 2. The diameter equals to AB equals to AD plus DB over 2. AD equals to 9 over 4. DB equals to 4. All divided by 2. Here we multiply 4 by 4 and then we divide it by 4 in order to have a common factor with 9 over 4. So 4 times 4 is 16, plus 9 is 25. And here in the denominator we have 4 and all divided by 2. So here we have 9 plus 16 is 25 over 4. 2 will go to the denominator and we'll get that in conclusion R equals to 25 over 4 times 2. 4 times 2 is 8, so in conclusion found out that the radius of the big circle, capital R is defined as the radius of the big circle, and it is equal to 25 over 3 units. Here, the radius of the big circle, that is to say capital R, equals to 25 over 8 units. Okay, then we actually defined the center of the big circle as point P, and we defined the center of the small circle as point Q. And then from the center of the small circle, that is to say from point Q, we draw radius that is drawn to the point of tendency. Here the radius QL, that is equal to small r according to our definition. It is drawn to the point of tendency, that is to say it is drawn to point L, that is the point of tendency of tangent CD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CD will be perpendicular to the radius DQ. The tangent CD will be perpendicular to the radius LQ. So CD is perpendicular to LQ. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from point Q, we draw radius to the point of tendency, that is to say, to point M. So here we have the radius QM that is drawn to the point of tendency, that is to say, it is going to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is going to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent DB will be perpendicular to the radius MQ. Again, DB is perpendicular to MQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So, in the next step, we focus on quadrilateral LQDM. In a quadrilateral LQDM, we have here we have 1, 2, 3 right angles plus this angle that we don't know the size of it. So we know that 3 angles are right angles, 1, 2, 3. The sum of 3 right angles is 90 times 3 is 270 degrees plus the size of the fourth angle, that is angle LQM. So here 270 degrees, that is the size of 3 angles plus the size of the fourth angle, that is angle LQM. In total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, we subtracted 270 degrees from this equation and found out that the missing angle LQM equals to 360 degrees minus 270 degrees, it is 90 degrees. So this angle, it is a right angle, is equal to 90 degrees. That is to say, we found out that all 3 angles inside quadrilateral LQDM are right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral LQDM as a rectangle. Okay, here I wrote down that quadrilateral LQDM is a rectangle. Quadrilateral LQDM is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle LQDM, its opposite sides are equal to each other. That is to say LQ equals to DM. According to the rule that the opposite sides of a rectangle are equal to each other, we'll get that in rectangle LQDM, LQ equals to DM. But we have already found out that LQ equals to R. LQ equals to R, it is the radius of the small circle. So from this equation, R equals to LQ equals to dm, we will derive that dm is also equals to R. Okay, dm is also equals to R. Okay, and then we found out the length of the small line segment dp. Here dp, what is the length of dp? dp equals to db minus pb. Again, dp equals to db minus pb. db minus pb equals to dp. Again, dp equals to db minus pb. db equals to 4 units according to what is given as the question. dp, oh, here, actually, pb, here, dp equals to 4 units according to what is given as the question, and pb, what is the length of line segment pb? P is the center of the big circle. P is the point of the big circle itself. This is exactly the definition of a radius. That is to say, pb equals to the radius of the big circle, that is capital R. Very simple. So in conclusion, we found out that dp, that is equal to db minus pb, equals to 4 minus capital R. So dp equals to 4 minus r. We already found out that r equals to 25 over 8. So we substituted r by 25 over 8. So in conclusion, we found out that dp equals to 4 minus 25 over 8. We multiplied 4 by 8 and then we divided by 8 in order to have a common factor with this expression. And there 4 times 8 is 32. So we have in the numerator 32 minus 25 over 8. 32 minus 25 is 7. So in conclusion, dp equals to 7/8. So here we can find out that the small line segment, the length of the small line segment equals to 7/8. Okay? Then we found out the length of line segment PM. What is the length of line segment PM? PM equals to DM minus dP again. DM minus dP equals to PM. DM minus dP equals to PM. Okay, PM equals to DM minus dP. So PM equals to DM, that is the radius. We have already found out that DM is the radius, it equals to the radius of the small circle. Here, DM equals to small r, that is the radius of the small circle. And dP, we have already found out that dP equals to 7/8. So in conclusion, we found out that PM equals to R minus 7/8. Okay? Then I presented to you rule number 2. According to rule number 2, the straight line that connects the centers of two circles with an internal length between them passes through the launch point, that is the point of tendency. So here we have the straight line PQ that connects the centers of the big circle, that is point P, and the center of the small circle, that is point Q. So line segment PQ connects the centers of the two circles, and this line segment PQ passes through the launch point, that is point S. Point S is the launch point, and according to rule number 2, line segment PQ must pass through the launch point, that is point S. That is to say, PQS is one straight line. PQS is one straight line. So we know that P is the center of the big circle, S is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PS equals to capital R. That is 25/8. While Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS equals to the radius of the small circle, that is small r. In conclusion, we found out that PS equals to capital R and QS equals to R. And what is the value of PQ? PQ equals to PS minus QS. Okay, here PQ equals to PS minus QS. PS equals to capital R. QS equals to small r. So in conclusion, we found out that PQ equals to capital R minus small r. Capital R equals to 25/8. So PQ equals to R, that is 25/8 minus small r. So in conclusion, we found out that the hypotenuse PQ equals to 25/8 minus small r. And we have already found out that PM equals to R minus 7/8. And QM is the radius of the small circle because of the fact that point Q is the center of the small circle and point M is the point on the semicircle, on the circle, on the small circle itself. This is exactly the definition of radius. So QM is the radius of the small circle, that is small r. Okay, now we implemented, I drew the right triangle QPM in this new page, and we implemented the Pythagoras theorem on this right triangle, triangle QPM. So by PT is the Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, according to the Pythagoras theorem. The hypotenuse is QP. The square of the hypotenuse is QP square or PQ square. This is the same. It is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to PM square plus QM square. Okay. PQ equals to 25/8 minus R. So we substitute PQ by 25/8 minus R. PM equals to R minus 7/8 over 8. So we substitute Pm by R minus 7 over 8. And Qm equals to R. So we substitute Qm by R. And we got this equation. We open the brackets on both sides of this equation, equation number 1. And we found out that 25 over 8 minus R square equals to 625 over 64 plus R square minus 2 times 25 over 8 times R. This is the value of this expression. After we open the brackets, on this expression also. R minus 7 over 8 square equals to R square plus 49 over 64 minus 2 times R times 7 over 8 plus R square. We have R square on both sides of the equation, so R square will get cancelled. And we left only with 625 over 64. Here we have, we divided both the numerator and the denominator of this expression by 2. 2 over 2 is 1. So in the numerator we have minus 25R. In the denominator we have 8 over 2, that is 4. So in conclusion, this expression equals to minus 25R over 4. And here, this is equal to 49 over 64 minus, here we divided both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1. So in the numerator we left only with minus 7R. And the denominator we have 8. 8 over 2 is 4. So in conclusion, this expression equals to minus 7R over 4 plus R squared. We multiplied this equation by 64. And we found out that here 625 times 64 is 625. And here we have 64 over 4, or minus 64 over 4 is minus 16. So this expression will be equal to minus 16 times 25R. This expression equals to minus 16 times 25R. In the other side of the equation we have here 49 over 64 times 64 is 49. Here we have 49. And here we have minus 64 over 4 is minus 16. So this expression equals in total to minus 16 times 7R. And here R squared times 64 is 64R squared. Okay? Then 16 times 25 is 400. So this expression equals to 400R. So in this side of the equation we have 625 minus 400R. That is equal to 49. And 16 times 7 is 112. So this expression equals in total to minus 112R plus 64R squared. We subtracted 400R from this equation, equation number 1. So this side of the equation, 400R minus 400R is 0. So we left only with 625. On the other side of the equation, we have 400R minus 112R, that is 288R plus 64R. We subtracted 625 from this equation, equation number 1. And we got that 625 minus 625 is 0. Here we have 49 minus 625, 49 minus 625 equals to minus 576. And we also have here 64R squared plus 288R. So in conclusion, we found out that according to equation number 1, 600R squared plus 288R minus 576 equals to 0. We divided this equation number 1 by 32, and we got that 64 over 32 is 2, so this expression equals to 2r squared. In total, 288 over 32 is 9, so this expression equals to 9r in total, and minus 576 over 32 equals to minus 18, that is equal to 0. So we have a quadratic equation. The coefficient A in this quadratic equation equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 3. The variable that we are looking for in this quadratic equation is r. So x equals to r, and the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Okay, here x equals to r, so we substitute x by r, and r equals to minus b equals to 9, so minus b is minus 9 plus minus b squared. B is 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 18, over 2a. A is 2, so 2a is 4. So here r equals to minus 9 plus minus 81, and 2 times minus 18 is minus 36, and minus 36 times minus 4 is plus 144. So in conclusion, inside the root we have left only with 81 plus 144, all divided by 4. So here 81 plus 144 is 225, so inside the root we left only with 225. So in conclusion, we found out that the radius of the small circle small r equals to minus 9 plus minus square root of 225 over 4. The square root of 225 is 15, so r equals to minus 9 plus minus 15 over 4. So here we have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r equals to minus 6, that is a negative number. But because of the fact that r is the radius of the small circle, so that is to say r is a length, as a length it must be a positive number. Therefore r can never be equal to minus 6, that is a negative number. So we cancel this solution, and we left only with the second solution for r, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4. Here we divided both the numerator and the denominator of this expression by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of this small circle, equals to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. I'll repeat again. R, the radius of this small circle, equals to either 3 over 2 units, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.